So in order to figure out, in the first video we found the moment of inertia of a rod about a fixed end, about one end. So now let's consider the moment of inertia about a rod in the center. So let's consider the moment of inertia about a point in the middle. Okay. So we still use the same formula, the moment of inertia. We're now going to do it about the y, or about the, let's call it the center of the rod. It's still going to be equal to the integral of r squared dm. Right? And how does that look? We still use the same thing. As long as this is uniform density and this is some length L, we're still considering the fact that the uniform density here, that this differential piece of mass, wherever we want to choose it, this little differential chunk, there's a whole bunch of those little chunks, right? We're going to think of this as a row of dimes, if you will. That might be helpful. We're going to add up all those little differential pieces, right? And each one of those has a linear mass density of dm over dx, which is also equal to the entire mass of the rod over the length of the rod. And we can substitute in, right? And you think, man, this is exactly the same as we did the last time, which it is in terms of the integration. The one thing that's very different, actually I'd like you to think about it. I'll take a little pause here, and I want you to think about what is going to be different for this particular problem. We're still only using x, so we're going to, r squared is x squared. This is going to be lambda dx. So what's different? Okay. If you recall, in the last time that we did this, we were asking about the point here, the fixed end of the rod to the other tip. So our limits of integration was 0 to L, right? The exact same thing that we did before. Here, this is the exact same expression, x squared ml over dx, or m over L times dx. But the limits of integration now are different. We're starting from the 0 point is here in the middle, and so the left end is minus L over 2, and the right end is plus L over 2. And so those become our limits of integration, which you may think that doesn't really matter, right? It's still over the same length, but the fact that we're integrating over different limits now is going to change our answer substantially. We'll see just how that is. The mass and the length are constant values. We can pull those out of the integral. This is just x squared dx. That's going to equal mass over length times 1/3 x to the third, from minus L over 2 to positive L over 2. And substituting those in, we get m over L, 1 divided by 3, times L over 2 to the third power, minus L over 2, sorry, minus a minus L over 2 to the third power. Now that seems a little tricky, right? We're taking the upper limit minus the lower limit. So this is a minus sign that comes from the fact that we're plugging these things in. Just like we had in the previous problem, we had L to the third minus 0 to the third. Here we get the upper limit minus the lower limit. Since the lower limit also has a minus sign in it. And because we're taking this to the third power, that minus sign doesn't go away. So these minus signs will end up canceling one another. So we get m over L times 1/3 times L to the third over, this is cubed, takes L to the third power and 2 to the third power. So we get L cubed over 8 plus another L cubed over 8. Because this minus sign is minus 1 to the third power, which gives us still a minus 1, times minus 1 gives us 1. And when we multiply this out, we get L squared. This is L squared, and, oh, I see what, something was screwy here. So what is this? We get m over 3 times 2L over 8, right? Here's an L over 8, and here's an L over 8. You can think of this as being 1/8 and 1/8. Will give us 2/8 times L. And then when we finally solve that last little part, this is 2 divided by 24, gives us 1/12 ml squared. There should have been a squared here. The L on the bottom canceled the one of the L's from the top in each of these. So we get 1/12 ml squared. The really impressive part of this is that we could actually determine this in a much easier step. There's something in your textbook that we might have a chance to talk about tomorrow, depending on how class goes, called the parallel axis theorem. And what the parallel axis theorem says, that you can figure out what the moment of inertia is about any point if you can figure out the moment of inertia of the center of mass of an object plus m times h squared. So the mass of the object times h squared, where h squared would be the following. So if we have some odd-shaped thing and we determine that its center of mass is at this point right here, this is the center of mass, and we can determine the moment of inertia about the center of mass is some quantity, then if we move some distance h away from that center of mass, we can determine what the new moment of inertia is about this new position by simply taking the moment of inertia about the center of mass plus the mass of the object times h squared. Right? So let's actually check that out and see if that's the case. So the center of mass of a rod is at the center of the rod. So this is the moment of inertia. Not only is it the moment of inertia about the center of mass, it's the moment of inertia about the center of mass of the rod, is 1/12 ml squared. So when we set this equal here, we get 1/12 ml squared. And let's say that we want to move from the center of mass to the outside edge. How far would we need to go? So we're going from the center, right? We're going from the center position of this rod out to the very edge. So that's a distance of L/2. So we're going to add on the mass of the object times L/2 squared. That's what h is in this for our situation of the two rods. So this gives us 1/12 ml squared plus 1/4 ml squared. And now we have to add fractions, right, with different denominators, and this is always really, really scary. So we just need to get a common denominator. Which is going to be 12. We multiply the top and the right term, the top and the bottom by 1. That special 1 though, 3/3, means the bottom we get 12 and the top we get 3 ml squared. The top we add together, we get 4 ml squared over 12, and then we divide through and simplify this, and we get 1/3 ml squared, right? And that's the moment of inertia about the end point, which is exactly what we set out to show, right? We showed that the moment of inertia for any point along an object can be determined by the moment of inertia about its center of mass plus its mass, the mass of the object, times whatever the distance it is that you're interested in. And you can do that for anything, any object whatsoever. So that's something, a very useful tool and very applicable for lots of different situations.